Hello and welcome to another Arlington High School Math 4 Honors lesson. I'm Kirk Weiler, and today we're going to be looking at Unit number 7, Lesson number 6, our second day on one-dimensional motion. Alright, so in our last lesson, if you recall, what we're going to be keeping track of is either the horizontal position of an object as a function of time, or the vertical position of an object as a function of time. And what we had last time, very, very simple, was we had the concepts of displacement, which was the change in position. We had average velocity, which was the displacement divided by the elapsed time. And most importantly, we had instantaneous velocity, which now we're just going to call velocity, which was the derivative of the position, and it told us how fast the position was changing and whether the position was increasing or decreasing. Excuse me. All right, so today, though, we're going to introduce some new ideas. And the first one we're going to get into is speed. All right? Speed is simply the size of velocity, the size of it. So we're just going to forget about the direction. All speed is the absolute value or the size of the velocity. What's interesting is a lot of classic physics formulas, and one that's good to know about is E equals 1/2 m times v squared, right? 1/2 mv squared. Well, you don't square vectors. It really doesn't make any sense to square a velocity. But it does make sense to square the speed because it is a scalar quantity. It's simply the absolute value of velocity. All right. And of course, that makes it very, very easy to use. Watch. Let's take a look at exercise 1. Given an object moving along the x-axis that has a position formula given by that quadratic, where the position is measured in centimeters, pay attention to the units, right? And time is measured in seconds, again, pay attention to the units, right? We want to give the object's speed, not its velocity, but its speed at 1 second and at 5 seconds. Include proper units. If you already feel comfortable with everything, why don't you go ahead and do this? You should be able to take care of it. So pause the video now. All right, let's go through the speed. Well, speed's the absolute value of velocity, so the first thing I'm going to do is figure out the velocity function. Right? Why not? Be awfully helpful. The velocity is the derivative of position, right? So that's going to be a simple power rule, 4t minus 8. So the velocity at 1 second is 4 times 1 minus 8, and that, of course, would be -4 centimeters per second. Now, that's not the speed, right? Speed's easy enough. Speed would be the absolute value of v of 1, which would be a +4 centimeters per second. Absolutely the same unit. All right. V of 5, on the other hand, well, that would be 4 times 5 minus 8. 20 minus 8 is 12 centimeters per second. And, of course, then the speed would be the same because the absolute value of that positive number remains positive. All right, so it's simple enough. In fact, typically, when asked for the speed, the only mistake kids make, and lots of them make this, is confusing it with the velocity. So watch out for that. If you have a multiple choice question where they give you the position and they say, hey, what's the speed at t equals 7, or what have you, then your answer's got to be positive. In fact, you can eliminate any of the negative answers that are there. I mean, it could also be 0. Exercise number 2, what information do you lose with speed that you know with velocity? So think about that for a minute. Pause the video if you need to. All right, real important. You lose information about direction, right? So speed still tells you how fast your position is changing. If I say that I am moving at a speed of 60 miles per hour, it means that my position is changing at 60 miles for every hour. What you lose is whether or not your position is increasing or decreasing. You lose the direction of travel. And that is really important, right? Speed is a scalar. It tells us nothing about direction. It only tells us about size. And that's important to know. All right, I'm going to clear out the text here in a moment, so copy down anything you need to, and then we're going to move on. Okay, here we go. All right, we have a random problem here. Let me bring something in. We're now going to talk about acceleration, the rate of a rate. I tell you, that sounds a little bit familiar. Sounds like a little second derivative action going on. The rate of a rate, right? Formally speaking, acceleration is the rate at which the velocity, not the speed, it's the rate at which the velocity changes, and it's defined mathematically very easy. The acceleration is the derivative of velocity. It's that simple. All right, it's really, really important to understand that. You see, what acceleration is going to do is tell us whether velocity is increasing or decreasing. That's what it's going to do for us, right? That's what the first derivative also always does. Technically speaking, and I think I should throw this out here, because velocity is the first derivative of position, acceleration would then be the second derivative of position, and that is a very, very important fact in a lot of physics and engineering. We won't really use it almost at all. Maybe we'll see it a little bit, but not much, okay? The most important thing to know is that the acceleration is the first derivative of velocity. So whatever first derivatives have ever told you, acceleration now tells you that about velocity. That's the same as velocity telling you about position. Whatever first derivatives tell you, that's what velocity tells you about position. So let's jump right into it. Exercise 3. An object has a vertical position given by y of t equals sine 2t minus 4t squared, where the position has units of feet and time has units of minutes. Okay, so feet and minutes. Find the velocity, speed, and acceleration, all at t equals pi over 4. Include proper units with all three answers. What I'm going to do is ask you to pause the video right now and see if you can work through this entire problem, including the units of acceleration, which are a bit tricky, and then we're going to talk about it all. Okay, so pause the video now. I would say take up to about 10 minutes to work through this problem. Okay, let's take a look. Well, first things first, if we're going to get velocity, we have to find the derivative of position. So we have to find dy dt. Okay. Sine of 2t, we would find its derivative using the chain rule. It would be cosine 2t, but then it's going to be multiplied by 2. And then, of course, the derivative of 4t squared is no problem. That's 8t. What I'm going to do is figure out what this is at t equals pi over 4. So that's going to be 2 times the cosine. Now, if I do 2 times pi over 4, I get pi over 2 minus 8 times pi over 4. Cosine of pi over 2 is 0. 2 times 0 is 0. We can simplify this a little bit, and we'll get negative 2 pi. The units, very simple, right? The units of dy are feet. The units of dt are minutes. So negative 2 pi, strange as that might sound, feet per minute. Fair enough? All right. The speed, of course, that's very simple. Speed's going to be the absolute value of v of pi over 4. So that's going to be a positive 2 pi feet per minute. All right, let's talk acceleration. So the acceleration is going to be the derivative of velocity, dv dt. All right. Now remember, let me circle it in red so that it really kind of stands out. Here's our velocity function. All right. So the first thing I need to do is take the derivative of 2 times cosine 2t. All right. No problem. I'll ignore the 2 for a little bit. The derivative of cosine is negative sine. And because of that 2t, I have another 2 involved. Now the derivative of negative 8t, which we don't want to forget, is negative 8. So if I clean this all up, we have negative 4 times the sine of 2t minus 8. So now if I want my acceleration at pi over 4, right, substituting that in, we'll get negative 4 times the sine of pi over 2 minus 8. That was weird. I just put in the sine of pi over 12. I said the sine of pi over 2, but it became a 12 down there. Who knows? Right, the sine of pi over 2 is 1. Negative 4 times 1 is negative 4. Minus 8 is negative 12. All right, so that's the numerical answer. Now for the units. Now I know that a lot of people watching this video have already had physics, so you're probably very trained in terms of the units of acceleration. But I don't need any training. Here's what I need to do. I need to say, well, the numerator is the change in velocity, so it will have units of velocity. And what were those? Feet per minute. The denominator is a change in time. So it's going to have units of minutes. So the final answer here is negative 12 feet per minute per minute. Now, I really prefer, this is me, I prefer units of acceleration to be written that way, right? Because it really gives you a wonderful feeling for what's going on. In other words, I can interpret this by saying that the velocity is decreasing at a rate of negative 12 feet per minute, right? And that makes sense. What physicists will often do is that they'll collect these two units. Now remember, feet per minute could also be thought of as feet per minute times 1 over minutes. So that's going to be feet per minute squared. So we could also state the answer as negative 12 feet per minute squared. The thing that I do not like about expressing the units that way, and if you work long enough in physics, you would probably write them that way because it takes less room, is that you lose sight of the interpretation. In other words, this is supposed to be telling you how fast velocity is changing and in what direction. So it's very strange to say that velocity is decreasing at a rate of 12 feet for every square minute. Number one, feet, that doesn't make any sense. It doesn't make any sense. You know, it's like saying my bank account is decreasing by llamas. I don't have llamas in my bank account. It can't decrease by that. Velocity can't decrease by feet, right? And the second problem is, what's a square minute? You know, I know what a square foot is. I know what a square mile is. I don't know what squared time is. So I don't care either way, but I like the interpretation of feet per minute per minute. So I'm going to erase this. All right, so take a look. Okay, let's move on to the next page. Now, of particular interest often in applied problems is figuring out whether an object is speeding up or slowing down, right? Because sometimes we're speeding up, sometimes we're slowing down, right? Kind of depends. Okay, so one of the fundamental things that we need to answer, one of the fundamental misconceptions that we should try to get rid of before it even takes root, is why acceleration alone can't tell us whether an object is speeding up or slowing down, right? And then it says perhaps consider why the sign of what the sign of acceleration does tell us. So think about that for a moment. Pause the video and ask yourself, what would I know if acceleration was positive? What would I know about the motion? What would I know if acceleration was negative? What would that tell me about the motion? So think about that for a bit. All right, let's come back to it. See, the problem is, if I know that the acceleration is positive, then what I know is that the velocity is increasing. And if I know that the acceleration is negative, well, then I know that the velocity is decreasing. But velocity and speed are not the same thing, right? Velocity is a vector, right? So what we're really getting at is the size of it. And I don't really know whether the size of velocity is increasing or decreasing just because velocity is. And you might say, well, come on, if velocity is going from 2 to 7, well then obviously it's getting bigger. But what if velocity is going from -2 to 0? Right? Velocity is getting bigger, it's increasing, but its size is actually decreasing. Did you catch that? And if we had a velocity that was, let's say, -3, let's say feet per second, and it changed to a velocity of 0 feet per second, well, velocity went up, right? If I go from -3 degrees Fahrenheit to 0 degrees Fahrenheit, I'm not happy, but at least the temperature's going up. But the speed's actually going down because it's going from 3 to 0. All right, so this is tricky. It's really tricky. Most importantly, acceleration alone cannot tell us if an object is speeding up or slowing down. Acceleration alone can't tell us that. That's going to be a mistake many of my students are going to make, so I dare you not to. Do not use acceleration alone. So what we're going to do next, after I clear out the text, is we're going to develop a way to figure this out. All right, now this is a very cramped problem, and I apologize for sort of like putting it all on one screen, but I really wanted to get it in here. We're going to take a look at an object's motion, all right? And all we're going to be given is the velocity graph versus time. I guess time must be in seconds if velocity is in centimeters per second. All right, and this is a great problem to do all together because it really starts, solidifying a lot of things that we've learned about motion. What I'd like you to do is answer letter A. Pause the video right now and think about this. Okay, let's talk. Is the object initially moving forwards or backwards justify? A lot of students will look at this graph and they'll make a mistake. They'll go, look at that. Well, the object's moving forwards. The velocity graph's getting bigger. But ironically, of course, the answer is the opposite. The object is moving backwards. And the explanation is simple. V of 0 is -8, and that's less than 0. Right? Velocity controls the direction of motion. Velocity controls the direction of motion. The sign of velocity tells us whether or not the position is increasing or decreasing. An increasing position, positive velocity. A decreasing position, negative velocity. All right, real important. Letter B, at what times does the object change direction? Now, I want you to really think about that. We've answered this question before. Changing direction. What controls whether or not we're moving in one direction or another? So think about the times when the object changes direction. All right. Again, some people might say 3 and 6 and 8, but they'd be wrong. The object changes direction at t equals 2 and 7 seconds, and it's very simple because v of t changes sign. Right? When velocity is negative, in here, the object's moving to the left. When velocity is positive, which is in here, the object's moving to the right, assuming that we're horizontal motion, and moving to the left again. Don't be fooled by sort of the fact that, oh, we've got this piecewise linear that's, that's going up and then plateauing, then coming down. No, no, no. Basic ideas. Velocity controls direction. The change in the sign of velocity indicates a change in direction. All right, let's take a look at letter C. It says, determine the value of A of 1, the acceleration at 1 second. Include proper units in your answer. Well, we know acceleration is the derivative of velocity, but we don't have a formula. So pause the video and think about another way you might be able to figure out A of 1. All right, let's do it. Figure it out. It's not too bad. A of 1 must be the slope of v of t at t equals 1. That's not that hard, right? It's right here. I need to figure out its slope. Well, I could actually just figure out the slope between these 2 points. I could say, well, the rise was 8, the run was 2, so the slope all along that line must be 4, right? So A of 1 must be 4. For what? Well, the change in y was in centimeters per second. The change in x was in seconds. So our acceleration is 4 centimeters per second. Definitely must be positive, right? Velocity is increasing, and if velocity is increasing, acceleration must be positive. So part D asks us to sketch a graph of the speed function on the same axes. I'm going to sketch it in green, but I'd like you to pause the video right now while I do some erasing. You pause, and then we'll graph the speed. All right, let's graph some speed. Well, we know that speed is the absolute value of velocity. So, whenever velocity is negative, speed is positive, right? So like when velocity was that -8, speed must have been 8. So in fact, all we really have to do, I meant to do that in green. Nuts. Very technical. Nuts. Right? All I have to do to graph speed is make sure that anytime velocity is positive, I just leave it alone. And anytime velocity is negative, I change it to be positive. So there's my speed graph. All right, simple enough. Now, the final set of exercises, E and F, get at how to know whether speed is increasing or decreasing. So we're going to develop a test, and it's so beautiful that when we get done with it, it should make all the sense in the world. All right. So at 4 isolated times in this table, 1 second, 2.5 seconds, 6.5 seconds, and 7.5 seconds, I want to figure out 3 things. Is the velocity positive or negative? Is acceleration positive or negative? And is speed increasing or decreasing? Okay, so positive, negative on the first 2 rows, and increasing, decreasing on the next one. So let's go back to t equals 1. Let's do this in red. Okay, t equals 1 is right here. And I'm fairly certain that the velocity is negative down there, right? On the other hand, I'm also pretty certain that the acceleration is positive because velocity is increasing, right? On the other hand, this is where I would be on the speed graph, and it definitely appears that the speed is decreasing in there. So what I'd like you to do is I'd like you to try to fill out the rest of the table for 2.5, 6.5, and 7.5 seconds. Go through that analysis, all right? And then we'll summarize our findings, but pause the video now. Okay, let's do it. At 2.5 seconds, we are right here. And at that point in time, the velocity is positive because it's above the x-axis. The acceleration is positive because velocity is increasing. And speed is also increasing. Whoops. All right, where's 6.5? 6.5's right here. Okay, in this case, what? Velocity is positive. Acceleration's negative because velocity is decreasing. And the speed's decreasing. All right, and 7.5 would be right here. So at that point, velocity is negative, right? Acceleration is negative because velocity is decreasing. But look at this. Here we're on the speed. And we're increasing. So I feel like I'm just about out of colors. Yeah, we'll just go black. Let's look at where speed's increasing. Speed's increasing here. And speed's increasing here. Now what do they have in common? So this is really letter F. We're going to use this space right up here. So speed will increase when A and V have the same sign. Both positive, both negative. And of course, we can also point out, now let's go blue, that here we've got the decreasing and different sign. So speed will decrease when A and V have opposite signs. I absolutely love this test because it really gets at the nature of vectors. You see, vectors can sort of work with each other or work against each other. Both acceleration and velocity are vectors. At the end of the day, right, what we're really saying is that when velocity and acceleration work or act or however you want to think about it in the same direction, then speed gets bigger. And to me this makes sense, right? If I've got an object that is, let's say, moving to the right and being pulled to the right, I always think of acceleration as a pull, a force. So I have an object moving to the right and being pulled to the right, then it's speeding up. If I have an object moving to the right but being pulled backwards, then it's slowing down, right? On the other hand, if I have an object that's moving to the left, negative velocity, and being pulled to the left, negative acceleration, then the object's speeding up. If I have an object moving to the left, negative velocity, but being pushed to the right, well, then it's getting slowed down. Right? So when velocity and acceleration work together, speed increases. When velocity and acceleration work opposite, speed decreases. It's really kind of cool. Watch out. This is a very common question on the AP exam and in general calculus classes. Students give the darndest answers. I'm telling you, my least favorite, but also kind of most favorite from a really perspective is when I ask whether speed is increasing or decreasing, and students calculate the speed, and then they say, speed's increasing because speed's positive. Problem with that is that, well, speed for the most part is always positive unless it's 0. So what that would imply is that if you have positive speed, then speed is increasing. That would mean that anything that's moving whatsoever, which by the by is everything, would just be getting faster constantly. Not going to happen. Of course, the most common error is people just say, well, based on acceleration alone, speed's increasing or decreasing, but we can't do that. We can have a positive acceleration with speed increasing. We can have a negative acceleration with speed increasing. Just look at that table. All right, I'm going to scrub out the text, and then we're going to finish up the lesson, so copy down anything you need to. I'm going to try to scrub out the text. There we go. All right. Well, that has been our second day on one-dimensional motion. We're going to spend one more lesson on it. That's going to be it. It's going to be kind of a fun lesson. Actually, I think two more. And then eventually we'll be tackling two-dimensional motion. But before we do that, we have to bring in really, truly the idea of multi-dimensional vectors, and we just don't have those yet. But we will eventually. Anyway, I'm Kirk Weiler. Thank you for joining me again. And until next time, keep thinking and keep solving problems.